Okay, hello grade 10 students and welcome to a new video. In this video, we are going to explain lesson 13.1 periodic motion part 9. So characteristics of simple harmonic motion. The key characteristic of the simple harmonic motion is the acceleration of the system and therefore the net force are proportional to the displacement and act in the opposite direction to the displacement. We know that according to Newton's second law, F net is equal ma. So the net force is proportional to the acceleration. This is why if we consider the acceleration, also, and by default, we're gonna consider in the same time the F net. So here, the acceleration is proportional to the displacement as well as the net force is proportional to the displacement. This proportionality means that as we increase the displacement, also the acceleration will increase. In addition, they will have opposite direction, the acceleration and the displacement. Now, the period from the previous lesson, we learned that the period and frequency of a simple harmonic motion are independent of its amplitude. That's it. The amplitude is independent of the frequency and period and vice versa. So changing the amplitude won't affect the frequency or the period. According to the formula, the period is given by 2 pi over mk. So the amplitude is not appear here in our equation as well as in the frequency, which is given by 1 over 2 pi k over m. So we can say that changing the amplitude won't affect the frequency or the period in the simple harmonic motion, or for simplicity SHM. Now let's study the acceleration. In order to study the acceleration, we're going to consider a horizontal oscillator which is formed of block of mass m and spring of stiffness k, as we can see here. We have the block and the spring which with stiffness k. The block is connected to the spring and the other end is attached to the support, as we can see here. The other end is attached to the support and the spring from the other end is attached to the block. Now this system is forming what we call it the horizontal oscillator. The friction is neglected, so we're gonna neglect the friction between the surface and the object during the oscillatory motion. There is no any friction here. Now, in order to study the acceleration, first we need to determine the forces acting on the system. As we can see here, we shifted the object from the equilibrium position to the right with the distance x. So x here represents the displacement. Now, what are the forces acting on the system at this moment and during the motion? Now the forces are, since we have an object here, the first force will be the pull of gravity. So the first force is the pull of gravity, which is directly downward. The second force is, since we have a surface in contact with the object, we will have the normal push, which is perpendicular to the surface, upward. And finally, since the object is attached to the spring, as we can see here, this spring will subject a force known as Fs, or the tension force or the spring force. So whether if you use the letter Ft or Fs, both of them are accepted to represent the tension force or the spring force. You can use them here exchangeably. Now, as we can see here, the tension always points toward the equilibrium position. So at any moment, the Fs should be directed toward the equilibrium position. In other words, during the oscillation, if the object moves to this direction, so now the spring is compressed, the tension force, it won't be to the left anymore. Instead of that, we should draw it toward the equilibrium position. In this case, always the Fs should be directed to the equilibrium position. Now let's apply Newton's second law here, knowing that the Newton's second law is given by F net is equal ma, which means we must apply here on the left hand side all the forces acting on the system in order to determine the acceleration, knowing that according to our free body diagram, Fn is equal to Fg, equal in magnitude but opposite in direction, so they are cancel each other. No need to include the Fg and Fnet, or sorry, Fn in our equation anymore. Now the only force left here is the Fs. This is why, or the Ft. This is why I'm gonna write minus Ft is equal ma, and minus here means that the direction of Ft always opposite to the displacement. Now knowing that the Ft is given by k times x according to Hooke's law, so let's substitute here k and x. Now if we divide both sides over k, we're gonna cancel this from this. In other words, we can divide over m also. So m with m would cancel each other. Now since we are looking for the acceleration, it's better to isolate the acceleration. This is why I'm gonna divide both sides over m. As a result, m with m cancelled out, and we will get this equation. Now a here represent the acceleration in meter per second squared. The k is just the stiffness of the spring in Newton per meter. The mass is the mass of the block in kilogram, and finally the position x represent the displacement from the equilibrium, and it's given in meter. Now let's take a close look to this equation. A is equal minus k over m times x. As we can see here, x and a are proportional, which means if we increase the x, also a will increase. And also if we decrease the x, also the acceleration will be decreased. Now, the acceleration itself, it's considered to be a variable. It's not constant anymore. Why it's a variable? Because we don't have a constant value for the position. Each moment, according to this video, the position of the object varies, which means every moment we have a new position for the block, which means since we have a variable on the right hand side, this is constant and this is constant, this is why the acceleration also will be a variable. And the kinematics here cannot be applied in this situation. What do I mean by kinematics? The big five equations, such like the v is equal at plus v0, the x is equal x0 plus v0t plus half at squared. All of these equations are not applicable here, because this equation is assuming that the acceleration is constant, and in our case, in simple harmonic motion, the acceleration is not constant anymore. Now the obtained equation, this equation, is a linear equation with a negative slope because it has a general form y is equal mx plus b. Now y here, if we compare between the two equations, we will deduce that the y is just the a. So this is a along the vertical. The x is the x here along the horizontal. And finally, it's a linear equation with a negative slope. Minus k over m represent the slope, which is negative here in this particular case. And what about b? b here is 0 because in our equation does not exist. This is why this equation should be passing through the origin. And if we want to plot this equation in the graph, it will look like this. Now, the extremes point in this line or in this linear graph represent the minus x max and the plus x max. So the projection of this point, this extreme point here, represent the plus x max, which means the distance from the O to the plus represent the amplitude. The other extreme point represent the minus x max. Now this is the horizontal projection for each of these points. What about the vertical projection, which means this coordinate? So for this point, we have two projections along horizontal and the vertical axis. The horizontal axis, the projection of this point along the horizontal axis represent the x max. Now for the vertical one, the extreme point here represent the acceleration max. And it's plus because it's laying along the positive direction or y-axis or the vertical axis, but also we have here another value for the acceleration in the negative direction. Now the acceleration versus position graph is a straight line with a negative slope passing through the origin. The acceleration is 0 at O and maximum at the extreme position because at O there is no any acceleration here because the line is passing through this point 0, 0. 0 along the x is just the position, this is the equilibrium, and the 0 along the y represent the acceleration. So in summary, this graph or this line associated with points. Each point carries two data about the acceleration and the position. So this point, for example, holds the following information: x and a. If we are looking for x, we just project it along the horizontal, so this is the x that we are looking for. And if we are looking for the acceleration, we just project along the vertical axis to find the corresponding acceleration for that location or position. For the extreme points, these 2 points represent the x max, minus x max here, and plus a max. And for this point, it will be plus x max, but minus a max. Now at the origin, we have the 0, 0. The acceleration will be 0 at the origin as well as the position. But why the acceleration is 0 at the position? Because we know that at the equilibrium, the force, the tension force will be vanished. And as a result, the acceleration also will be vanished. Now, whenever we have calculated the slope by using rise over run, we're gonna apply delta A over delta X. Now, after we did the calculation, the final result will be equal to minus k over m according to the given equation. Because here, the slope is represent the minus k over m. Okay, let's start solving some applications regarding this topic. An object undergoes simple harmonic motion. For simplicity, we're gonna use the letter SHM to represent the simple harmonic motion. Which of the following can be an expression of acceleration A in terms of displacement m and the constant value k? We know that the acceleration and x, k and m are related to each other with this equation: a is equal minus k over m times x. So the correct answer will be B. Okay, application 2. The graphs show how the acceleration A of 4 different objects varies with their displacement x. Which of the following or with which of the object is undergoing simple harmonic motion? We know that for oscillatory motion or simple harmonic motion, the acceleration is related to the position with this linear equation. Now, according to this linear equation, the line should be passed through the origin, through O, and it should be negative slope. Also, it will be linear. This is why I'm gonna suspend this one and this one, because they are not linear. And for A, I will eliminate 8 because A, although it's a linear passing through the origin, but this is not negative slope. The slope here is positive slope. The only choice that verifies these 3 conditions, linear, through O, negative slope, is B. So B is the correct one. Question number 3. A mass of 400 gram, automatically we're gonna express the mass in kilogram. So it's 400 gram. In order to convert it into kilogram, we just divide by 4,000 and the answer would be 0.4 kilogram. It's connected to a spring on a frictionless surface. A spring constant K is given by 0.06 Newton per meter. What is the magnitude? So we are looking for the magnitude of the acceleration when the mass is 20 centimeter from the equilibrium. So when the position or the displacement is 20 centimeter. Also, this one is not the SI unit. Let me express it in SI unit by dividing the value over 100, and the x is equal to 0.2 meter. Now, in order to find the magnitude of the acceleration, we should apply this formula. The acceleration is equal minus k over m times x. The acceleration is equal minus the k is given by 0.06. The mass is given by 0.4. And the position x at 0.2. Now we just substitute all the values in the calculator. So minus 0.06 over 0.4 multiplied by 0.2, and the answer is minus 0.03. meter per second squared. According to the choices, none of them is equivalent to my final answer. But why this has happened? Is it because my calculation is wrong? No. My calculation is 100% correct, but the thing is, we need the magnitude. So we're gonna drop from the solution the minus sign because we are looking for the magnitude. Minus here stands for the direction. As a result, the correct answer would be positive, and the correct answer is A. The graph below shows the variation of the acceleration of the object with the displacement. So this graph, we have along the vertical the acceleration, along the horizontal the position. Let's double check the units. Here it's meter per second squared, or we can write it as meter seconds minus 2. And along the position or the horizontal axis, we have x in meter. Given that the mass is 2 kilogram, use the graph to determine the spring constant K. We know that the slope here has a specific meaning. Slope is equal minus K over M. So let me calculate the slope to find minus K over M. And then we're gonna use it in order to find K. So the slope is equal. So we're gonna pick up 2 points. I'm gonna take this one and the 0. So the first point, it would be, has the following coordinate, the minus 0.06 meter, and in the middle point between 4 and 6, in the midpoint between 4 and 6, we have here 5, so it will have a 5 meter per second as acceleration. Now, the second point is 0, 0. We're gonna start from the right side, y2 minus y1, x2 minus x1. So y2 is 5 or 0, you can start with 0 or 5. I'm gonna start with the 0, 0 minus 5, and since we took first the y coordinate from this point, I will take the x coordinate from this point also. So I would start with 0 minus 0. We have double minus here, minus from the slope formula and minus from the coordinate of that point. So it's equal to, let me use the calculator to find the exact value for the slope. 0 minus 5 over 0 minus 0.06. And the answer is minus 250 over 3. Now we know this value represents the minus k over m, so let me make them equal. So minus k over m, it's equal to the minus 250 over 3. Now we know what is the value of mass is 2, so let me substitute here 2, which is equal minus 250 over 3. Now we can multiply both sides with 2 to eliminate or to isolate the k, so times 2 times 2. Now 2 with 2 would cancel out. On the right hand side, we need to multiply 2 times 2 minus 250. So as a result, k is equal minus 250 times 2 over 3. So we just multiply this fraction times 2. So minus 250 times 2 over 3. And the answer is minus 16.6. So minus k is equal minus 16.6 Newton per meter. However, we have two minuses here, so we can cancel them because from the beginning we have two minuses from the fact that this is a negative slope and also this value should be negative. So don't forget to consider the minus again. Because the k cannot be negative, it's a constant, spring constant, and the answer would be k is equal 166.6 Newton per meter. The last question for today. So the acceleration versus displacement graph of an object performing simple harmonic motion or SHM is shown in the figure. Use the graph to determine the amplitude of the oscillation. Now the amplitude of the oscillation is defined to be the distance from the equilibrium to the maximum position. We know that the extreme points here represent the X max and A max. By project this point along the horizontal, we can find the plus X max. The distance between the O and the plus X max represent what? The amplitude. So the amplitude here in this case is 0.08 and the given unit is in meters, so the answer would be in meter. What about the maximum acceleration? We know that the other extreme point is associated with the minus X max and plus A max. So if we project this point along the vertical, we will have information about the A max. Now the A max here, according to this point or this coordinate, it's 8, and the unit is meter per second squared. So 8 meter per second squared. This is the A max. Find the ratio K over M. Then use its value to calculate the period. So we know that in order to find K over M, we can use the slope because the slope here is represent the minus K over M. So after we found the slope, we just take the positive value of it to find the K over M. So I'm gonna take 2 points. For example, we can take this one and the 0. So the first point will be minus 0.04 and 4. The second point is 0, 0. So this one is this one is this. So let me calculate the slope now. 0 minus 4, 0 minus 0.04. We plug it in the calculator to get the answer. So 0 minus 4, 0 minus 0.04, and the answer is minus 100. Now, what does the minus 100 represent? The minus 100 represent the value minus K over M equal minus 100. However, we are looking for K over M, not the minus 100. Or the minus K over M. This is why we just multiply by minus both sides to get the K over M. Now what will be the corresponding unit? The numerator has a dimension of spring constant, and for the denominator it will has the dimension of mass or kilogram. Or we can use this value and this value to determine the given unit. So here, let's go back one step behind. The unit for the numerator here is in meter per second squared, and for the numerator is gonna be meter. Now we can cancel meter with meter and we will end up with 1 over second squared. So the answer should be in 1 over second squared. Now, in order to find the period, we should implement this formula, M over K. However, we don't have what is the mass, what is the K. but we have information about k over m. So we can use this information in order to obtain m over k, because the m over k is the reciprocal of k over m. All that you need is to flip the answer upside down to get m over k, so it's gonna be 1 over 100. So k over m is equal to 100 over 1. Even if we don't have a denominator for the number, we just put the 1 as a denominator for any real value. Now, since we flipped the m up and the k down, we can apply the same thing for the 100 over 1. And the m over k in this case is going to be 1 over 100. So let me substitute here. 2 pi square root 1 over 100. As a result, the period is equal to, let me calculate the period now. So 2 pi multiplied by 1 over 100. And the answer is 1 over 5 pi. Or we can press S to D in order to find the decimal value for this number. And the answer is 0.628. If you want to approximate it, we're gonna write it as 0.63, and the unit will be second. So 0.63 second, this is the period of this oscillatory motion or simple harmonic motion. That's it for today. Thank you for watching.